All right, good morning, everyone. So I want to start off by rectifying a mistake that I made on Monday on this problem. So basically, we got to go back through what we did with the problem. So again, we argued that this force here is going to be the same as this force, which is true. Those two guys are equal and opposite, so they cancel, which means the only force is going to be on the wire. And I made it a point to say that the force was only going to point in the vertical direction. But if you go through your notes, when I then got to this point of the integral, I never had anything here that said I was only taking the vertical portion of the integral. That was where the mistake came in. So basically from here, what we simply said was that this was equal to IB times the integral of DL, but the integral of DL was simply R times the length, or in this case, what? It was pi R is what we said the length was. Now, the problem here, as I'm going to point out again, because I made this mistake, not you guys, but we only want to take the vertical portion. Because again, as we said, if we're looking at the force, so again, we point our fingers in the direction of the L, curled into the external magnetic field. So again, our force is doing this, which means again that all the horizontal pieces of the force are canceling, we only have the vertical piece. Which means the thing that we forgot last time was to put something in here that said I only want the vertical portion. Okay. So, as you'll find out, if we forget that, it changes actually completely the answer. We'll see that in just a second. So good. So what I need here is to now introduce a new angle. We've already used the angle theta because we said theta was the angle between the current and the magnetic field. But now I have to introduce another angle here to specify the fact that I only want the vertical portion. So now we have to introduce a new angle. So let me put in a new angle here. Let's call that angle phi. So now what I need is something here that specifies that I want only the vertical portion. So which trig term corresponds to only the vertical portion? Sine in this case, right? So I need to now multiply this by sine of phi. Now the problem here though, is if we think about the DL actually depends on phi, which means we can't pull this outside of the integral, we actually have to integrate over it. And the reason for that is, as I drew on here, we actually have an arc length. So this little tiny wedge here has an angle of d phi, which means DL here is actually equal to R times d phi. So using arc length, the little tiny width of this thing, DL, is the same thing as this constant radius of R times this thickness here, which is simply d phi. So this thing actually ends up becoming I times B times R times the integral of sine of phi d phi. So we actually have to integrate over that sine phi. Now here we're going to integrate from, the current is going, in this case, from 0 to pi. So we have to integrate this over the angle from 0 to pi. Okay, so this was the mistake I made last time. I apologize for that. Apparently my brain didn't start yet, but these things happen. Okay. So good. So this is a nice simple integral. What's the integral of sine? Negative cosine. So this is equal to negative IBR cosine of phi evaluated from phi is equal to 0 to pi. What's cosine of pi? -1. So this thing is a -1 minus a cosine of 0, but cosine of 0 is 1. So I get a -1 minus 1, which is a -2. But this negative sign now makes it positive. So this thing finally becomes the force is equal to twice the current times the magnetic field times the radius. In this case, all pointing in the j direction. Sorry about that. So this is what we actually should have got, not what I wrote down last time. Okay. Again, the problem here is that as I made it clear on that day, the only direction of the force is the vertical pieces because all the horizontal pieces cancel. What I forgot to put in last time was the sine of the angle here. I realized that yesterday, actually, I forgot to do that. So again, we have to integrate over that sine because, again, this arc length depends on that angle. So notice here we actually have two different angles. We have this angle here, and then we have the angle between DL and the magnetic field itself. So I just wanted to rectify that, just in case something like that comes up in the future. So that way we don't have quite a problem with that. So the last thing we talked about on Monday was all kinds of examples of the force on a charged particle. moving in an external magnetic field. So just to remind you, we have the force then is equal to the charge of that charged particle times its velocity crossed by the external magnetic field. Here, if I wrote this again as a magnitude, I would have the magnitude of the force then is equal to the charge times the velocity times the magnetic field times sine of the angle between the two. So here, if this was the velocity, this was then the magnetic field. Again, this angle here is the angle specifically between the velocity and the magnetic field. So we looked at mostly easy expressions of this because we had the velocity was moving perpendicular to the magnetic field. So the magnetic field pointed in one direction, the velocity was perpendicular to that. So what we said was that causes it to actually move in a circle. And anytime that it's actually not quite perpendicular, but like in this case, it's at an angle, what it will actually do is spiral around here. So this is going to move in a spiral of a fixed radius. So the next thing we want to start looking at is, well, what happens if our magnetic field now doesn't point in a single direction, but it points in multiple directions? And let's say we have a velocity which also points in different directions. So what I want to do then is determine how do I actually calculate this cross product if this is true. So now if I have a magnetic field pointing in multiple directions, velocity pointing in multiple directions, how do we actually do that? So first we'll do this in general. So let's say I have these vectors, which I'm given in component form. So I have vector A is AX in the I hat direction plus AY in the J hat direction plus AZ in the K hat direction. B and C then are basically the same. So just broken up in component form. So what I want to know then is, how do we actually then determine the cross product A cross B equal to C? So the way that we do that, and anybody in Calc 3 can tell me how do we do this, is we determine the determinants of a matrix. Okay, so basically what we're going to do is we're going to set up a 3x3 matrix, where in the first row here is the directionals. So I have I, J, and K. The second row then is the first vector. So the components of the first vector. So A, X, A, Y, and A, Z. And then the third row then is the components of the second vector. So the way that we actually do this is determine or use what's called the determinant. So the way the determinant works is we're going to cross off this column with this row. And then I'm going to take everything and multiply by this value that I crossed off. Then we take what's known as the determinant of the minor matrix. So what's left then is this little section here, which is what's called a minor matrix. So the way this works is this is equal to then I times the determinant of the minor. So the way the minor works is I'm going to take this guy times this guy minus this guy times this guy. So I'm going to get a AY times BZ minus then BY times AZ. That's my first component. Now I'm going to do the same thing. So let me use a different color. So let me use green. So now I'm going to cross off this column in this row and multiply everything by this guy. But this guy is a little bit special. He actually gets a negative sign put in front of him. So this is actually going to be minus J times. Now I'm going to do the same thing. So now I have a minor matrix made up of this column here with this column. So I'm going to take this guy times this guy minus this guy times this guy. So this is going to become AX times BZ minus AZ times BX. Okay. Finally, let's do it one more time. So I'm going to cross off again this same row, but now this column, and I'm going to multiply everything by this term. So I get a plus K times now the determinant of this minor matrix here. So the same thing, I'm going to take this guy times this guy minus this guy times this guy. So I get an AX BY minus AY times BX. So these are the components from this cross product. So again, we're just going to set up this guy. But simultaneously, this has to be equal to C, where C is equal to CX in the I hat direction, plus CY in the J hat direction, plus CZ in the Z hat direction, or the K hat direction. Which means that if I compare the left-hand side to the right-hand side, all of this stuff here is simply CX. So by looking at this, we can then say, well, CX then is equal to AY BZ minus AZBY. Comparing then CY then has to equal all of this stuff. I'm going to bring that negative sign on the inside. So I get CY then is then equal to AZBX minus AXBZ. And then finally, CZ then must be equal to AXBY minus AYBX. So these are the components of this vector, created then by these other two vectors. Okay. Now, if you've never seen this before, or you're not comfortable doing this, all you need to do is write this expression down. So just write these three things down. Make sure they show up on your note card if it comes to an exam, so that way you know where they are, in case you can't reproduce the cross product. So for our case, since our cross product looks like F, which is actually C, is equal to Q times B, which B is the same thing as A, cross B. So what this means for us then is that F of X is then equal to Q times, so this is going to be what, Vy dz minus Vz By. And we're going to get Fy then is equal to Q times, so I get an AX, AZ Bx minus Ax Bz. And finally, Fz is then equal to Q times Ax By minus Aybx. So again, if you really don't know how to do a cross product, just make sure you write these things down on your equation card and keep them there just in case. Here's okay? So this is how we would actually determine a cross product in general. So in case my magnetic field didn't point in just one direction, my velocity pointed in multiple directions, and etc. So let's use this and let's do an example. So this says I have a proton which moves through a uniform magnetic field, which is given by B is equal to 10I minus 20J plus 30K all millitesla. Then it says at some time t1, the velocity vector then is given by Vx in the I hat direction plus Vy in the J hat direction plus 2 kilometers per second K hat direction. And the force is measured to be 4I plus 2J times 10 to the minus 17th newtons. So we want to know at this instant, so meaning at time t1, what are the velocity components Vx and Vy? So this is what we want. What are Vx and what is Vy? And those are our solutions. So let's go back. So here, what do we know? We know Fx, we know Fy, and we know Fz. Fz is simply 0. We know Vz, so we know that term there. And I wrote that as an A, it should be a V. Sorry about that. So this should be a V. That should also be V. And I'll count up at A's. There we go. V, there we go. So we know that. What else do we know? We also know the components of the magnetic field, which means that all we have to do then is solve these three equations then to determine the two unknowns. Now, if I only have two unknowns, how many equations do I need to solve? 2, right? So that means one of these is redundant. I don't have to use all of them. Now, in this case, the simplest thing to do would actually be to use the fact that this is equal to 0 to then write a relationship between Vx and Vy. Which means that when we use the other equation, when we find, say, Vx or Vy, we can then simply plug it into that one, and then we automatically know the other term. So it's probably easiest to do it that way. So let's use that. So first, let's use the fact that 0, because Fz is equal to 0, is equal to Q times Vx Vy minus Vy times Vx. Since this is equal to 0, we can easily divide out the Q and then solve for, say, Vx. So this tells me that Vx then is equal to Vy times then the ratio of Vx divided by Vy. So this is Vx. From here, all I then have to do is determine, well, what is Vy? So how are we going to get Vy? Well, for example, we can use the first equation. So here we can isolate Vy because we know Vz, we know Vz, and we also know Vy. So we can finally solve for that guy. So let's use that. So here we can say that Fx is then equal to Q times, so this is Vy Vz minus Vz Vy. Let's divide everything by Q. So this gives me Fx divided by Q is equal to Vy Vz minus Vz Vy. Finally, what I want is Vz, so I'm going to add the second term to both sides. So I get a Vy Vz is equal to Fx divided by Q plus Vz Vy. And finally, all I want is Vy, so I'm going to simply divide everything by Vz. So I get Vy then is equal to 1 over Vz times Fx divided by Q plus Vz times Vy. From here, let's go ahead and plug in our numbers. So we go back to our question. We look up what Bz was. Bz for us was equal to 30 millitesla. So let's plug that in. So it's going to be 1 over 30. So that's 0.03. Right? Milli is 10 to the minus 3. Fx, so according to Fx, that's equal to what? 4 times 10 to the minus 17. Let's plug that in. This is 4 times 10 to the minus 17, and this is a proton, right? I make sure. Yeah, it's a proton. What's the charge of a proton? Not buried in your subconscious yet? No, it's a fundamental charge, so it is 1.602 times 10 to the minus 19. Thought that would come back and haunt you in your nightmares, but anyways, all right, so that's that guy. Good. Plus Vz, so let's go back to our question. So Vz then is equal to 2 kilometers per second. So that's 2,000 meters per second. That's 2,000 meters per second. Times By, where By then is equal to minus 20 millitesla, so that's times minus 0.2. Plug in our numbers, we find in this case then is that Vy, according to what I wrote on the slide, is equal to 7 kilometers per second. Great. So this works out to be 7 kilometers per second. Once I know that Vy is equal to 7 kilometers per second, all we're going to do then is go back to this one, plug in what Vy is times the ratio of those two, and this works out to be minus 3,500 kilometers per second. Just to make sure, yeah. Well, that's it. Nice and easy. So again, cross products. So in general, this is the way we'd actually do cross products. If those two things are perpendicular, it makes it a lot easier. In that case, we can write it in terms of the magnitude of each times the sine and angle between the two. But again, if in case I give it to you in component form, you have to use it this way. So again, if you're not comfortable with cross products, just make sure these things show up on your equation card when it comes time to do the next exam. Was okay? So the next thing we want to look at is what happens if I take a loop of wire, so a loop of current carrying wire, and put that in an external magnetic field. So this is what we want to know. So what happens if we take a loop of current carrying wire and put that guy into an external magnetic field? So let's first do a front view, show what we actually mean here, and then we'll do a side view as well, so we can talk about these things. So good. So front view, just to make this a little bit simpler, let's do a rectangular loop of wire. So here's my rectangular loop of wire. So let's call this side A and this side B. And let's say, in this case, we have currents running through it. It's going in this direction. So this is my current. Now we're going to put this into an external magnetic field, which is going to point, say, in this case, into the board. So this is my external magnetic field, which we're going to say is a constant. So magnitude of B here is simply a constant. So it's like points constantly in that direction. So that's our front view. Our side view then is going to be my magnetic field is going to point this way. So this is B. Draw a few magnetic field lines. So this is my B. And I'm going to take this wire and put it in my external magnetic field so that this thing is actually tilted at an angle. This guy actually looks like this. So this is the side view. So in this case, I'm looking at it from this side. So the side view is if I'm looking at it from this direction. So in this case, my current is running up through it in this direction. And this is side length A. So good. So let's talk about these things. So let's look at the front view for now. So what's going to happen then is I have basically 4 legs. Each one of these legs then is going to carry a force. We know the force then is going to be given by the right-hand rule, or in this case, we would point our fingers in the direction of the current. So in this case, I'm putting my fingers this way, curl towards the external magnetic field. So I have to rotate my palm, curl in this direction, which means the force on this side is going to be towards the center. So I'm going to call this force of right is to the center. What about from the top? The top, current points this way, external magnetic field is in this direction, so I put my thumb downward. So force top is going to be this way. So it's going to be F top. For the right hand or left hand side, current is moving down this way. Do it like that. External magnetic field is into, so my thumb is going to point again towards the center of this loop. So this is going to be force of left. And finally, for the bottom one, current is this way, external magnetic field is into the board, so my thumb is pointing towards the center. So I get then F bottom is pointing this way. I'll reserve the side view here for just a second. So let's think about each one of these forces. So what this says then is that the net force acting on my object is simply equal to the sum of all the different forces, which in this case then is equal to the force from the top plus the force from the left plus the force from the bottom plus the force from the right. Now, what I also know is that the magnitude of the force from the right is then equal to what? So let's go back. So here it's going to be I times the length, which in this case is A, times the external magnetic field times sine and angle between the two of them. Well, what's the angle between the current and the magnetic field? So if my current is pointing this way, magnetic field is pointing this way, what's the angle between those two things? #90, right? So this is the 90-degree angle, which means sine of 90 is simply equal to 1. So the magnitude of this guy is simply IAB. The force on the left is also IAB. The force from the top is then going to be what? IB, because this one has a side length of B, times the external magnetic field B, and then force on the bottom is also equal to IBB. But according to my picture, FR is in the opposite direction of FL. The magnitudes are the same, so these guys are equal and opposite, so they're actually going to cancel each other. So force right is the same thing as force left. Force top is opposite direction from force bottom. They both have exactly the same magnitude, so they also cancel, which means that the net force is simply equal to 0. So my net force on this thing is equal to 0. So what's happening is if this was my loop of wire, this thing is being pushed in this direction and pushed in on this direction, but it's being pushed equally this way and equally this way, which means it's not doing what? It is not accelerating. Meaning it's not moving this way or moving this way, or this way or this way or this way or this way. It's simply being crushed inward and crushed inward, but it's not accelerating. So it has 0 net force to it. So this guy has 0 net force. Well, let's look at the side view. Let's see what's going on with the side view. So notice here, what's happening is what? If I'm looking at this portion where the current is moving inward, so I pull my fingers in the direction of the current, curl towards the external magnetic field, so I have to rotate my palm this way, curl, so this force is actually pointing straight down in this direction. So if I look at F top from the side view, F top is actually pulling it this way. Okay with us? F bottom then is going to be pointing what? The current is now running towards you, so I put my fingers in the direction of the current, curl towards the external magnetic field, so I have to rotate my palm this way, curl towards the external magnetic field, my thumb now is pointing upward, which means that the bottom force is actually this way. So this is F top and F bottom. So because this thing is actually tilted like this in my external magnetic field, this force is pulling it downward, this force is pulling it upward, so this thing is going to do what? It's It's going to rotate, right? This thing is going to feel a torque. So the net force is equal to 0, but the torque certainly is not 0. So let's talk about the net torque. So the net torque then is going to be equal to what? The torque on the top plus the torque on the bottom. Let's talk about those guys. So let's look at the magnitude of the torque. So this is going to be equal to the magnitude of the torque on the top plus the magnitude from the torque on the bottom. So remember, torque is equal to R cross F. So let's go back to our picture. So in this case, what's going to happen is this thing is going to rotate about the center position, which means that R in this case is going to be half of this distance. So this is going to be R for this guy, where R for this guy is going to be half of this distance. Since this is side length of A, R then in this case is going to be A over 2. So for both of these cases, R, at least the magnitude of R, is going to be equal to A divided by 2. So this is going to be A divided by 2 times the force, where the force in this case is the magnetic force, times sine of the angle between the two. We'll talk about that angle in a second. And this one is also A over 2. So let's call this F top. This is going to be F bottom times sine of the angle between the two. Now, let's go back. What's the angle between the two? So in this case, my R vector points, let's look at this one, in this direction. So this is R. F is pointing downward, which means if I extend R in this direction, this then is the angle between the two. That's the angle theta. Now, what's the direction of the torque? Well, again, we would point our fingers in the direction of R, curl towards the torque, which means on this guy, the torque is in this direction. Here, I put my fingers in the direction of R, torque force is upwards, so I'm gonna rotate my hand this way, curl towards the force, my torque is also in the same direction, so those two torques are in the same direction. So that means that we would simply add these two guys together. I get up to plus that. Now notice that this angle here is the same as this angle, right? Because again, if I write R in this case is going to point this way, extend this guy here, then this angle theta here is exactly the same as that angle theta. Good. Now what? So good, so let's plug all this in. So we also know that F top is the same thing as F bottom, which means that those two magnitudes are exactly the same. So this thing is finally going to become A times F, let's say bottom, times sine of the angle between the two. Because these two things are the same. Here again, I know that the magnitude of F top is equal to the magnitude of F bottom. So I'm simply going to write it as F bottom. So this is F bottom, this is also F bottom, those two are the same, so I just get rid of that factor of 2. Good. Now, we also know, based on what we did before, F bottom is the same thing as I times B, so let's plug that in. So this finally becomes I times A times B times sine of the angle between the two. One more thing. What is A times B in this case? So let's go back to our picture. What is A times B? If I take this guy times this guy, what's that the same thing as? So think geometry. Area? Area! Fantastic. So I know A times B in this case is simply the area. So this finally becomes I times the area times B times sine of the angle between the two. I times A gets a special name, which is called mu, which is what's known as the magnetic moment. So mu here is the magnetic dipole moment. So I times A. Now, the presence of the sign, though, since torque is a vector, B is a vector, mu then must be a vector as well. The sign here means that this thing is actually a cross product. So here, we can then say that the torque is equal to mu crossed by B. This is the torque that's on this loop of wire. So what is mu? So again, mu vector is then equal to I times a vector. So we talked about this before when we talked about Gauss's law. What we said was that anything that has an area can be classified by a single vector which points perpendicular to the surface of this area. Okay. So in this case, what this means is, if this is my area, so this is A and this is B again, I can classify this by an area vector which either points this way or points this way. The question is, which one is true? The answer to that is the right-hand rule. We have a new right-hand rule to talk about. Right-hand rule number 3. So right-hand rule number 3 determines the direction of mu. So the way that this works is, step 1, we curl fingers in direction of the current. Step 2, thumb, which is perpendicular to our hand, points in direction of the area. So what does that mean? So that means if this was my loop of wire and I have current, say, running around it in this direction, so for you that would be in the clockwise direction, what you would do then is you would take your right hand or left hand? Right hand, good. And you would curl your fingers in the direction of the current. So in this case, my hand's curling that way. That's the opposite direction because I said it was going clockwise. So I'd have to curl my fingers in the direction of the current. So I would have to do that. My thumb at a 90-degree angle to my hand would point in the direction of the area, which in this case means the area would point towards me. The area then, because I is always positive, then points exactly in the same direction as mu as well. So this is actually in the direction of A slash mu. Those two are in the same direction. So good. So this is what we call the magnetic moments or the magnetic dipole moments. Now this is technically only true if I had one loop of wire, but what happens if I have multiple loops of wire? So let's say I had, this thing was made up of 10 loops of wire, all in this direction. Well, each one has exactly the same magnetic moment, so the total magnetic moment then would simply be the sum of all 10 of those magnetic moments, which all point in the same direction. So if I had more than one loop, in general, then my magnetic moment then is going to be equal to n times I times A, where n here is equal to the number of loops. So this is actually the more general expression. This is the magnetic moment. So let's go back to our picture. If we use our picture then, let's use the side view. What's happening here is my current is going in this direction, or if I use the front view, my current is going this way. So the way we would determine then the direction of mu is, again, we curl our fingers in the direction of the current. Our thumb would then point in the direction of mu, which means when I'm looking at it from the front view, mu then is pointing out of the board. If I do it from the side view, mu is curling, or I is curling in this direction, so I curl my fingers in this direction. Mu then would point in the direction of my thumb, so it actually points in this direction. So here, mu then would point this way. This is mu. The angle then, theta, is the angle theta between the magnetic moment here and the external magnetic field, which is actually this angle here. So this is the angle of theta. And if we were very particular about our geometry, we would notice this angle is the same as this angle, which is the same as this angle. So all those angles are actually the same. So what this thing wants to do then is it wants to create a force to then pull on this guy so that what? This magnetic moment is going to move itself to align itself with the external magnetic field. Since this thing has a torque, it also has an energy. So let's talk about its energy. The potential energy then is equal to minus the magnetic moment dotted by the external magnetic field. This is the potential energy. So what this thing says, again, is if my loop was like this, magnetic moment is pointing this way, magnetic field is pointing this way, what it wants to do is it wants to align the magnetic moment in the direction of the magnetic field, since that is the configuration of the least amount of energy. Everything wants to seek a lowest energy. So this thing is simply going to rotate until this portion is true. Now notice, if we go back to what we talked about with electric dipole moments, remember that the torque for an electric dipole moment was the magnetic moment crossed by the external magnetic field. The energy was equal to minus the moment dotted by the electric field, where here we're finding that the torque on a magnetic moment is equal to the magnetic moment crossed by the external magnetic field, and the energy is equal to minus the moment dotted by the external magnetic field. These two have exactly the same structure. This is not by accident. So identical structures. Only difference was this one was two charged particles, negative, positive, Q, moment pointed from the negative charge to the positive charge, external magnetic field pointed this direction. This also felt a torque, did exactly the same thing. So the magnetic moment is exactly the same thing as the electric dipole moment, and it has exactly the same structure and does exactly the same thing. Okay? So let's do a couple of examples. My first example says, not that. Okay. Determine the magnetic moment of an electron orbiting the proton of a hydrogen atom at a given instance, assuming that the electron is in its ground state, which means that the circular radius of orbits at which it undergoes is 0.529 times 10 to the minus 10 meters, which is also called 0.529 angstroms, which is what's also known as the Bohr radius. Now, what this is assuming is the planetary model of the electron. So here what's happening is I have a proton. Here's my proton. I have an electron, which is orbiting my proton at some fixed radius of r. Now, is this what actually happens? Hell no would be my answer, but anyways, no. We know that the planetary model is actually completely not correct, but we're gonna go with this anyways, because that's what this guy wants us to do. So what happens then is that what? The electron is gonna move around the proton, let's say in this direction. So I have an instantaneous velocity in this direction. So this is moving under uniform circular motion. So this thing is gonna move in a circle about some fixed radius of r. A single moving charge constitutes as a current. So what's happening is I have a current which is undergoing a loop, which means that this is a loop of wire in an external magnetic field, which is then creating a magnetic moment. So I have a current which is moving in an area, so therefore I have a magnetic moment. So in this case, we know the magnetic moment then is going to be equal to the current times the area. So what's the current? The current is, remember, the change in charge divided by the change in time times the area, but what's the area of a circle? Simply pi r squared, right? Good. So this one single charge moving around in a closed circle constitutes as a current. So the current in this case then is going to be the change in charge, which is simply the charge of the electron, divided by the time it takes for this electron to start at this point, go all the way back to this point. Well, how much time does it take to go from that point back to the same point? What do we call that by definition? Period. So this is going to be the charge divided by the period times pi r squared. How do we determine a period? Well, we know this thing is going to go through a 2 pi r worth of distance at a constant velocity of v in the time frame of a period. So this says then that the period is going to be equal to 2 pi r divided by that speed at which it's moving. So I know what r is. I know what 2 pi is, but I don't know what the velocity is. So the next thing we have to do then is determine what is the velocity. Well, the way we're going to do that is to use the net force. So let's think about the force. So we know the net force acting on this object must be equal to the mass times the centripetal acceleration, which in this case is mv squared over r. Because this thing is moving under uniform circular motion. Now, my question is, what's generating the force in this case? Is the electron moving around the proton because of gravity. Because the proton also has what's called an intrinsic spin, which means he also has his own magnetic moment, which means that he's in an external magnetic field. So is it the magnetic force, which is causing this thing to actually move around in a circle? Or what's the sign of the charge on the proton? Is that positive or negative? What's the sign of the charge on the electron? So is it then the electric force which is causing an attraction between these two? So we have three ultimate choices. So is it the magnetic force, is it the gravitational force, or is it the electric force which is causing the net force in this case? Technically they're all there, but one of them is so much more dominant than the other ones that we're going to ignore the other two. So which one is it? Is it going to be the magnetic force, the gravitational force, or the electric force? What do we think? What do we think? I'll give you a hint. It's not the one we learned last semester. So it is not gravitational. So it means we have two that we learned this semester. Which one is it? Which one do you think? Who wants to be brave? No, but good try. It's electric force. So what's actually happening here is the electric force is actually what's causing this guy to move in the circle. The problem in that, it's not the magnetic force because the magnetic moment of this guy is very small and so is magnetic moment of that guy. So it doesn't have a very strong magnetic field. So yeah, so it's actually the electric force which is causing this guy. So good, so we know that this is the electric force must then be equal to mv squared divided by r. Good, we know the electric force by Coulomb's law is then K, the electric constant, times the charge of the proton, which is the fundamental charge, times the charge of the electron, which is also the fundamental charge, so it becomes an E squared, divided by the radius squared, then must be equal to mv squared over r. Good, so this r is going to cancel out with one of those. What we simply want is the velocity, so let's go ahead and solve this guy for the velocity. So I'm going to divide both sides by m and take a square root. So we get the velocity then is going to be the square root of k times e squared divided by mr. So good, we can now plug that into our magnetic moment. Our magnetic moment then is going to be E divided by the period times pi times r squared. But again, we know the period is equal to what we did on the other page, 2 pi divided by the velocity, or 2 pi r divided by the velocity. So this is going to be E times v divided by 2 pi r times pi r squared. Now this pi cancels this pi, and I'm going to use this thing for v, so let's plug that in. So this is going to be EV, this r cancels out one of those, sorry, replacing. So this is E times r divided by 2 times the square root of k e squared divided by mr squared. So this then is my magnetic moment. From here, I plug in numbers. E here and here are both what? 1.602 times 10 to the minus 19. The radius here is 0.529 angstroms. So put those in. The mass is the mass of the electron. So that's going to be 9.11 times 10 to the minus 31. And then K is 9 times 10 to the 9th. So if we plug in all those values, we find in this case then is, it should be 9.27 times 10 to the minus 24. So it's equal to 9.27 times 10 to the minus 24. This thing has current units of amps, because that's a current, times an area, which is meters squared. So this is meters. Okay, what's up?
Why is your R value squared to the radical?
Oh, sorry. Thank you. Thank you, Isaac. I just got too excited. Was okay? Not too bad. Let's do another example. So the next one says we have a coil of wire carries a current of I is equal to 2 amps in a clockwise direction while looking down the y-axis is parallel to an xz plane, has 3 turns, and has an area of 4 times 10 to the minus 3 meters squared, and lies in an uniform magnetic field, which is given this way. So 2 minus 3 minus 4 millitesla. So I want to know, part A, in this orientation, so what is the energy, so the potential energy of the coil in the external magnetic field? And then finally, part B, I want to know what is the torque. So let's draw this thing. So what's happening then is, draw a pretty picture. So if I draw this as X, Y, and Z, what's happening then is I have a magnetic moment points in the Y direction. So this is the direction of my magnetic moment. And it says if I'm looking down the axis, I see it moving in the clockwise direction. So actually the moment would be, my fingers are control this direction, so my moment would actually be in the negative Y direction. So here I have mu is pointing this way because I is moving in the clockwise direction. Okay? So again, if I'm looking down the y-axis, so if my y-axis is pointing this way, it says here's my loop of wire. My current then is moving in the clockwise direction this way. So I curl my fingers in the direction of the current. My thumb would then point in the negative y direction. So that's why that thing points negative y. Okay? Now what we're told is that this thing then, mu, is going to be equal to minus I times A in the j hat direction. I is given to us and A is also given to us, so we just need to know the direction. Good. This thing is now going to be in an external magnetic field. So for part A, we then know that the energy is equal to minus mu dotted by the external magnetic field. So this is going to be equal to minus I A J dotted with the external magnetic field, which was Bx in the I hat direction plus By in the J hat direction. We move this over. U is equal to minus I A J dotted with Bx I hat plus By J hat plus Bz K hat. Now, remember, dot product picks out anything which is parallel to it. So this guy dotted with this guy is going to give me 0. This guy dotted with this guy gives me non-zero. And this guy dotted with this guy gives me 0, which means the only component which actually survives is then the J component. So this negative sign kills off this negative sign. So this is going to be equal to I times A times simply By. Okay. Plug in our numbers. This was then 2 amps is the current times the area, where the area is equal to 4 times 10 to the minus 3. So this is 4 times 10 to the minus 3 times the magnetic field component, where By was equal to negative 3 millitesla. So this is minus 3 times 10 to the minus 3. So because that negative sign is going to then make it a negative. So this is the same thing as what? 10 to the minus 6 times 12. So I have 12 to the negative 6 times 2, which is then 24. So negative 24 times 10 to the minus 6 joules. So that's then the potential energy. Is okay? Finally, we can do the torque. So part B, we know the torque then is equal to the magnetic moment crossed then by the external magnetic field. So this is the same thing then as I times A with a negative J crossed by Bx in the I hat direction plus By in the J hat direction plus Bz in the K hat direction. Now again, we know that a cross product picks out anything which is perpendicular to it, which means the J and the I, that thing is non-zero because they're perpendicular to each other. J with J is 0 because those two are parallel, and J with K is also non-zero. So those are also not going to give me 0. So this is going to be equal to then minus IA Bx times J cross I minus IA Bz times J cross Now, just to remind you, if I do I, J, and K, if I go in this direction, everything then is going to be positive. So here I have a J cross I. So if I do J cross I, that's equal to negative K, because I'm going in the wrong direction. So this is going to be equal to I, A, B in the K hat direction. Here I have a J cross K, so that's a positive I. So this is going to be minus I, A, B, Z, then in the I hat direction. Plug in our numbers, what we find out to get then is, as this thing says, we get 9.6 in the I hat direction plus 4.8 in the K direction times 10 to the minus 5 newton meters. So this is what we get after plugging in. Okay. So good. If I put a loop of wire in an external magnetic field, this thing has an energy and it has a torque. So this thing is going to rotate itself so the magnetic moment points in the same direction as the magnetic field. And it has an energy associated with that as well. So tomorrow, we're going to look at why do we actually know it's electrons which move in a wire and not protons? What was the experiment that actually told us that? That experiment's what's known as the Hall effect. So we're going to start looking at the Hall effect. After that, we're then going to start looking at how do we actually calculate magnetic fields? So far, we only looked at forces and torques. So how do we actually calculate magnetic fields? So the way we're going to do that is we're going to look at the equivalent of Coulomb's law, and then we're going to go to the equivalent of Gauss's law. So we're going to look at both of those two things. So. Have a good night. That thing.
So why do we, I thought, okay, so like one of the, those simulations, I don't know if it's one you use, but the one from the PHYS206 simulations, there's a circuit one and it has, it'll show like conventional current and flow of electrons. So like what is conventional current? Like,
Yeah, conventional current is the direction in which the positive charges would be moving. And then the actual version is that the electrons actually move in the opposite direction. So that's right. So if you're thinking about, say, going through this direction is the curve. So if we said the curve is going this way, that would be the direction of the positive charges moving. But in reality, what it actually is the negative charge is moving in the opposite direction.
yeah.
And we can actually see that through, so if you remember the